Dear students, today we will continue with the previous lecture, that is non-inertial frames of reference. So far you have learned that a frame of reference which has an accelerated motion is called a non-inertial frame of reference. And due to this non-inertial frame of reference, a pseudo force or a fictitious force comes into play. This is not a real force, but it comes into play because of the accelerated motion of the non-inertial frame of reference. Now, how do you understand that? Suppose we have a particle, an object at rest, and it is observed from an inertial frame of reference at rest. But if the same particle is observed from a non-inertial frame of reference, which is moving with certain acceleration, what happens? That for this observer, this particle seems to lag or move behind with an acceleration minus a. So the consequent force is F is minus times ma. This force is a fictitious force because this is not acting on the particle in reality, but it appears to be because of the accelerated motion of the non-inertial frame of reference, right? Now you have to learn one more thing, that the direction of the fictitious force will always be opposite to the direction of motion of the non-inertial frame. In case of the example of a lift, I have told you that if the lift moves upwards, the direction of the fictitious force will be downwards. Similarly, if the lift moves downwards, the direction of the fictitious force will be upwards. If the non-inertial frame of reference moves forward, the force appears to act backward and vice versa. In short, we have to remember that the direction of the fictitious force or pseudo force is opposite to the direction of motion of non-inertial frame, right? Now, I also told you that a rotating frame of reference can also be treated as a non-inertial frame of reference, because even if it is moving with a constant angular velocity, there is always a centripetal acceleration associated with this frame, due to which it is non-inertial frame, right? Now, a beautiful example of this kind of non-inertial rotating frame is Earth. Earth is rotating around the sun. It is revolving around the sun. It is also rotating about its own axis. The revolution gives rise to the years, and the rotation about its own axis gives rise to days and nights, right? Now, the angular velocity of rotation of Earth is denoted by omega, and obviously this is equal to 2 pi by t. So that is 2 pi. In case of rotation of Earth, the time period is how much? Just 1 day. That is 24 hours, 60 minutes, 60 seconds. So whatever is the value in radian per second, that is the angular velocity of rotation of Earth, right? Now, one more important thing with respect to non-inertial frames is that the particle or the object under consideration can be at rest or it can be in motion. Now, the fictitious force that appears due to this non-inertial frame on a particle at rest is called as a centrifugal force. Centrifugal force. And that is given by m omega square r. Remember, the numerical value of the centrifugal force is the same as that of centripetal force. We know that centripetal force is mv square by r. All of us know that. We also know what is the relation between the linear velocity and the angular velocity, that is v is equal to r omega. If we substitute that here, that is equal to r omega square by r. So that is m omega square r. So this force is numerically the same force as centripetal force, but the direction of centrifugal force is opposite to that of centripetal force. While as the centripetal force is directed radially inwards, centrifugal force is directed radially outwards. Radially outwards. Right? So this is the fictitious force, again I am repeating, which acts on a particle due to a frame of reference for the particle at rest. Now, let us see what is the fictitious force that appears due to a rotating non-inertial frame of reference on an object which is itself in motion, and that force is called as Coriolis force. Coriolis force is given by minus times 2m omega cross v, where omega is again the angular velocity of rotation of the non-inertial frame, v is the velocity of the moving object, m is the mass of the same object, right? And what is this r here, by the way? It is It is the radius vector that joins the position of this object with the origin of the rotating frame, right? Of course, in a subsequent video, I'm going to show you in detail the scheme of derivation of this force and this force. But at the moment, you just need to get introduced to this concept, right? Now, we will also have to consider what will be the effect of this Coriolis force on the motion of the object on the surface of Earth and on the motion of the object that are projected from the surface of the Earth. Now, this is the Earth. It's rotating about its own axis. Remember, the direction of rotation of Earth is from west to east. Remember, west to east. By west, we always mean the negative direction of x-axis. By east, we mean the positive direction of x-axis, right? So the Earth is rotating from west to east along its axis, right? Now, the component of, or the angular velocity omega of Earth is taken to be along YZ plane. Remember, in the YZ plane. See, you should remember one more fact, that Earth is not rotating about its own axis like this, but it is also tilted. So, Earth is not a sphere of this type which is rotating, but it is a sphere which is a bit tilted also along the axis, right? So, essentially we find that the resultant angular velocity of Earth is falls in the YZ plane. So, this omega is taken in the YZ plane and not along the x plane, right? Therefore, you can write this omega as omega xi plus omega yj plus omega zk. Since we treat this omega x equal to 0, omega is essentially omega yj plus omega zk. And remember, omega y is omega cos lambda j plus omega sine lambda k. Now you may ask me, what is this lambda? This lambda is called the latitude. Latitude is the angle which the radius vector of the, suppose this is the body lying on the surface of Earth. The radius vector that joins this body to the center of Earth makes certain angle with the equator. And that angle is called lambda, or it's also called as latitude. It is also called as latitude. So these are the components of omega. Omega cos lambda j along y-axis, omega sine lambda k along z-axis. But it will not have a component along x-axis. Now, I may assign you a numerical problem. For example, we have a bullet that is fired with certain velocity, say 500 meters per second. We will have to find what is the Coriolis force that acts on the bullet if it is fired in the eastward direction, if it is fired in the northward direction, if it is fired in the southward direction, if it is fired in the westward direction, and so on. We can choose all possible directions. But before solving these examples, these numerical problems, we should try to understand the concept of this Coriolis force a little better, a little further. And what is that? Since we know that this Coriolis force is basically how much? Minus 2m omega cross v. We know 2 is a constant, m is the mass of the object or the bullet in this case. We have to expand this component, omega cross v. And how do we write omega cross v? It is this I, j, k. For omega, since omega x is 0, omega y is omega cos lambda, omega sine, this y is omega sine lambda. For v, if the object is moving on the surface of Earth, it will have two components, vx and vy, and vz will be 0. But for such motions in which you are dealing with the objects that have been thrown in outer space from Earth, only vz component will be there. Vx and vy will not be there. So, for motion of missiles, rockets, spaceships, etc., this determinant will get changed. This will be I, j, k, 0, omega cos lambda, omega sine lambda, 0, 0, but vz. One more thing that you need to know is that if the object is moving eastward, remember, x-axis depicts the motion in the eastward and westward direction. Vx will be taken positive if the body has to move eastward. Vx will be taken negative if the body is moving westward. Vy will be taken positive if the body is moving northward. Vy will be taken negative if the body is moving southward. In this case, Vz, if the body is projected up from the surface of Earth, Vz will be taken positive. And for case of falling bodies which return back to Earth, Vz will be taken negative. That's all. That's all. Once we are knowing all this, we can proceed to solve the numerical problems. Now let us go to this numerical problem. So, suppose in this case you are asked to find what is Coriolis acceleration. Coriolis acceleration. And we can find acceleration only in this case, because to find the Coriolis force, we also need to know what is the mass of the bullet that we are not given. So we can find the Coriolis acceleration. And what is Coriolis acceleration? That is the same thing without mass. That is minus 2 omega cross v, right? Omega cross v can be found from this. Now what is the value of Vx? Because in the first case it is eastward, so Vx will be taken as 500. Vy will be taken 0, this will be taken 0, right? There is no component in the y direction. Now omega, I have already told you that it is 2 pi by 24 into 60 cos lambda, right? So cos lambda, you will also be provided with certain angle. I'm just giving you certain approximations, then you will be able to solve the numerical problems. It's not a big deal. So you will be asked in the question, it will be provided to you that the bullet has been fired at this much of angle with respect to the horizontal, right? Its velocity is this much and it has been thrown in the eastward direction. So what is the value of the Coriolis acceleration? And you can find it from this, right? Vx will be given a value, say 500. Vy will be given a value 0. This is already 0. Omega is 2 pi by 24 into 60. And lambda is how much? For example, the bullet has been fired at certain angle, say 45 degrees. So lambda is 45 degree. Cos 45 is 1 by root 2. Sin 45 is 1 by root 2. So you can find it. That's quite easy. Similarly, in case of a rocket, suppose if I tell you at certain missile, certain rocket has been fired with a velocity 2 kilometer per second. And of course, we should expect higher values of velocity here. It is 2 kilometer, that is 2000 meter per second. So essentially you are going to give this value to Vz, and you will also be told that at which angle with respect to the horizontal is this rocket projected, so that you will substitute for lambda, right? Omega is already known to you, so you can find the value of acceleration or Coriolis force. That's quite easy to find. One more important thing that I would like to add to your knowledge is what is the direction of Coriolis force? Direction of Coriolis force. Remember that in the northern hemisphere, the bodies tend to turn right on account of Coriolis force, and in the southern hemisphere, the bodies tend to turn left on account of Coriolis force. Now, let me take up the example one by one. For example, this is my student, and he is moving in the northern hemisphere. But moving in the northern hemisphere can mean two things. Either he is moving towards north or he is moving away from the north. Now let us take each case one by one. Now once the student is moving towards north, that means his back is towards me. So this is the right of student and this is left. He is moving towards north. And then what do I say? That on account of Coriolis force, his motion will be deflected towards right. Towards right means this. And what is that? That is east. So if the student is moving, if the object, if the bus, if any person, any object is moving towards north in the northern hemisphere, the effect of Coriolis force will be that his motion is deflected towards east. Now if the same student is moving from north to south in the northern hemisphere, again I say that in the northern hemisphere, his motion will be deflected towards right. Now once the student is moving from north to south, he's facing me, right? At that case, this is the right of the student and this is the left. And when I say that his motion will be deflected towards right, that means towards this side, and that is west. And that is west. Similarly, you can find it here. When any object, a person, anything is moving in the southern hemisphere, on account of Coriolis force, its motion will be deflected. In the southern hemisphere, it will be deflected towards left, and in the northern hemisphere, it will be deflected towards right. Now, similarly, to quote it once again, this is my student, and now he is moving in the southern hemisphere. Now, let's take the first case. In the southern hemisphere, the student is moving towards south. That means he is facing me. This is his right, and this is his left. And I say that he will be deflected towards left. And what is the left? That is east. Now, when the student is facing towards north, he is moving towards north. In that case, this is the right of the student, and this is the left, because now his back is towards me. His back is towards me because he is moving towards north. This is his right, and this is his left. And again, I say that since he is moving in the southern hemisphere, his motion will be deflected towards left, and towards left means towards west. Towards west. So, there are deflections towards east or west in the northern and southern hemisphere, but in each case, in north it means towards right, in south it means towards left, right? So this, I hope that gives you a fair idea of centrifugal force, centripetal force, Coriolis force, and these are all very relevant forces in case of Earth as a non-inertial frame, right? Some more examples that you need to take into account are direction of cyclones, direction of trade winds that move along the surface of Earth. Their motion, their direction also gets deflected on account of Coriolis force. Similarly, when you project rockets or missiles in the outer space, you have to take care of the deflection due to Coriolis force. Due to Coriolis force. And what is that? For example, if this is Earth and I am at this point and I have projected a rocket in the outer space, I intend to hit here. But during the time I project this rocket, Earth has rotated certain distance. So it is very likely that the rocket may hit here and I may miss my target. Therefore, I have to prehand incorporate those corrections in the mathematics, right, to hit the target straight away. Therefore, those corrections are already incorporated before we project a missile or a rocket or a spaceship in the outer space, right? So these are some of the important applications of Coriolis force. And in the subsequent video, I'm going to show you in detail the scheme of derivation that leads to the expressions for Coriolis force and centrifugal force. And again, I'm repeating that do remember these determinants for solving numerical problems. Vx indicates the direction along the x-axis. Vx is positive for east, negative for west. Vy is positive for north, negative for south. And z is the velocity if the object is thrown up. It is taken positive if the object is thrown up and negative if the object falls back to earth, right? Omega, I have already told you that it is 2 pi by 24 into 60 into 60. Lambda is the angle which the radius vector of the object makes with the equator of Earth, right? So all the components are clear to you and you can easily solve numerical problems that are asked with regard to Coriolis force. That's all.